Let us now record some more lemmas. So say you are given a map from topological space A to X. This map is K. And then you have two homotopic maps from X to Y. So these two homotopic maps are F and G. And then you have a map H from Y to B. Now if we are given that F and G are homotopic, this would imply that HF is homotopic to HG. That is, you first apply F and then H. This is homotopic to first applying G and then H. And if you first apply K and then F, this is homotopic to first applying K and then G. So let us show this. So first, since F and G are homotopic, we have a homotopy between them. So say H is that continuous map which takes X time I to Y. So this is the homotopy from F to G. So that is H of X comma 0 is F of X and H of X comma 1 is G of X. Then we have a new homotopy which is H, small h composed with this capital H. So the new homotopy we have is you first apply capital H and then small h, and this homotopy makes HF homotopic to HG. So you can simply see this. You first plug in 0, you get H of F, because H of X comma 0 is F, and this X comma 1 will give you G. Now we show the second part, that is Fk is homotopic to Gk. So this is done. Now we have to do this part. So let us draw the figure first. You first apply K, then you go to X times I, where this capital I is the unit interval. So capital I is unit interval from 0 to 1. And then you apply the homotopy map. So H of K comma X comma 0, this will automatically give you F of K of X. So which is F composed with K, and then you have H of K of X comma 1. So this will give you G of K of X. So this is a good candidate for homotopy. So now we have to precisely define what this homotopy is going to be. So this homotopy you can write as H of K of X times ID on I. So you have K and then times ID on this unit interval 0 to 1. So that will give you the continuous map. So you feed in space capital X, that goes to map K, and then you feed in the interval, and that just gets picked up directly by the ID map. So more precisely, you have H of K of X comma T, where T lies in the unit interval and X lies in the space A actually. So this is the required homotopy. Now another lemma we want to prove is, so this was number 2. Number 3 we want to show is that this homotopy equivalence, the homotopy equivalence we talked about, this is an equivalence relation on topological spaces. So homotopy equivalence is an equivalence relation on topological spaces. So first recall the definition of homotopy equivalence. So you have two spaces x and y, and you have maps between them. You have a map f which goes from x to y, and you have a map g which goes from y to x. So homotopically equivalence means that you have homotopic maps which are, you first apply say f and then you apply g. This should be homotopic to id on x, and then if you first apply g and then you apply f, this should be homotopic to id on y. So notice that this homotopy equivalence is essentially weakening of homeomorphic spaces. In homeomorphic spaces we would probably have equality there rather than homotopy. So reflexivity and symmetry are just encoded in the diagram itself. Yeah, g naught f and f naught g, homotopic to identities, that covers reflexivity and symmetry. So we have to talk about transitivity. So say x is homotopic to y and then y is homotopic to z, then we have to show x is homotopic equivalent to z. So you have space x, you have space y, and you have space z. So x is homotopically equivalent to y. That means you have the maps like this, f and g, and you have first g, then f is id on y, and then g naught f will give you id on x, and then y is homotopically equivalent to z. So you have to have further maps, say h and k. So you first apply k and then you apply h, you get id on z, and then you first apply h and then you apply k, you get homotopically equivalent to id on y. So notice that you immediately have map from x to z, which is given as h naught f. That is, you first apply f and then h, and then you have map from z to x, which is given by you first apply k and then g. So you have g composed with k. So we need to show these maps, that is, you first apply h naught f and then you apply g naught k. This should be homotopic to id on x. Yeah, you can see you first travel from x to z and then travel back to x. Similarly, you first travel from z to x and then travel back to z. So you first apply g of k, travel to x, and then back to z via h of f. Now notice that this k composed with h, this is id on y. This is homotopic to id on y. So when you compose g with it, you just get g of f, which is id on x given here. Similarly here, look at F composed with G. This is homotopic to ID on Y. So you put homotopic here, and then you are just left with H and K, which is homotopic to ID on Z, and that is given to us.